तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last two lectures, we saw about recurrence relations and how to solve those recurrence relations or difference equations by finding the homogeneous solution and also the particular solution. Depending upon the type of the equation, we have to find out the homogeneous solution. Then depending upon the right hand side FR, we have to decide what type of particular solution we can have and then solve it. The solution to the recurrence relation consists of the sum of both the homogeneous solution and the particular solution. This is what we have seen in the last lecture, and we get an expression for AR, the rth term. And this we can also get by means of using what is known as generating functions. Earlier we have seen how generating functions can be used for finding the permutations and finding the combinations and so on. We saw both ordinary generating functions and exponential generating functions. Here what we will consider is only ordinary generating functions. How the idea of a generating function can be used to solve the recurrence relation. So, this is what we will see today. Let us take this example. So, we want to see the solution by the method of generating function for the recurrence relation. Take this example. Consider the recurrence relation AR is equal to 3 AR minus 1 plus 2 is equal to plus 2. This is true for R greater than or equal to 1. So, A1 is equal to 3 A naught plus 2, and the boundary condition is given as A naught is equal to 1. This recurrence relation is valid only for R greater than or equal to 1. You can see that if R is equal to 0, this recurrence relation becomes A naught is equal to 3A minus 1 plus 2, and A minus 1 does not have any significance, it does not exist. So, this particular recurrence relation, it is valid only for R greater than or equal to 1. Why we have to consider this particularly here will become evident in a moment. Now, given this, you multiply by ZR both the left hand side and the right hand side. Multiplying both sides of the equation by ZR, you obtain AR Z power R is equal to 3 AR minus 1 Z power R plus 2 Z power R. Now, sum it over all R greater than or equal to 1. Here the reason comes, you cannot sum it for R greater than or equal to 0 because it is not valid for R is equal to 0. So, you have to sum for all R greater than or equal to 1 because it is valid for those values of R. So, if you sum it for all R, you obtain sigma R is equal to 1 to infinity AR ZR equal to 3, this 3 you can take out, 3 sigma R is equal to 1 to infinity AR minus 1 ZR plus 2 times sigma R is equal to 1 to infinity ZR. Now, what is this left hand side? See, the generating function for A naught, A1, A2, A3 etc. is A naught plus A1 Z plus A2 Z square plus A3 Z cube and so on. So, sigma R is equal to 1 to infinity AR ZR is A1 Z plus a2z squared and so on. The first term a naught is not there. So, if you denote by az the generating function for this, then the first term is not in this. So, you have to subtract the first term. So, this is equal to az, which represents the generating function for this a naught, a1, a2 sequence, and because the first term is not there, you subtract that. Similarly, look at this portion, that is leave alone 3, later on we can add multiply by that 3. Consider this portion, r is equal to 1 to infinity ar minus 1 zr. Now, the generating function is a1z plus a2z squared and so on. So, general term should be ar minus 1 zr minus 1, it should be the general term, but here we are having a zr. So, 1 z you have to take out. So, if you take out 1 z from this, you will get sigma r is equal to 1 to infinity ar minus 1 zr minus 1, which is the general term for the generating function. It starts from r is equal to 1. When you put r is equal to 1, it becomes a0. So, all the terms are there, a0 n plus a1z plus a2z squared and so on, but you have taken 1z out. So, this becomes z a z. And if you look at this term, let us consider 2 later, but this is 1 plus, no, you have to start with r is equal to 1. So, it is z plus z squared plus z cubed and so on. But you know that 1 plus z squared etc. is 1 by z. Here again, if you take out 1 z out, this becomes 1 plus z squared plus z cubed etc. and that is 1 by 1 minus z. So, sigma r is equal to 1 to infinity is z by 1 minus z. Use these values in this equation, then you will get az minus a naught is equal to 3z az plus 2z by 1 minus z. But the boundary condition a naught is given to be 1. So, a naught you substitute the value of 1 here. So, az minus 1 is equal to this. So, bringing the 1 to this side and bringing this 3z az to the left hand side, you get 1 minus 3z into az equal to 2z by 1 minus z plus 1. If you simplify the right hand side, it becomes 1 plus z by 1 minus z. So, you get 1 minus 3z into az is equal to 1 plus z by 1 minus z. Again, bringing this to the right hand side, you get az is equal to 1 plus z divided by 1 minus 3z into 1 minus z. If you resolve this into partial fractions, then this can be written as a by 1 minus 3z plus b by 1 minus z and solve for a and b, you get this value. So, the general term here will be this, you can see that can be expanded as 1 plus 3z the whole squared and so on. So, the general term here will be 3 power r z power r. Similarly, here if you expand, it is 1 plus z square etc. So, the general term is z power r for this. Consequently, you get ar is equal to 2 into 3 power r minus 1. Now, look at this equation which we started with. ar minus 3 ar minus 1 is equal to 2. So, you can see that 3 is a characteristic root, and so a 3 power r will be a homogeneous solution, and so using the boundary conditions you can find that it is 2 into 3 power r, and this is the particular solution. This also you can very easily see. But we have obtained the same thing by the method of generating function, and this seems to be a better method, because in the case of finding the homogeneous solution in the particular solution, you guess the value of the particular solution and try to substitute in the equation and find the exact particular solution. But when you use generating function, there is no guessing or anything, you have to straight away consider the equation, sum it up and then get the answer. So, what is the general procedure for determining the generating function of the numeric function a from the difference equation? It is a linear difference equation of the kth order. C naught, C1, C2, Ck are constants, and you have this equation C naught AR plus C1 AR minus 1 plus C2 AR minus 2 and so on equal to Fr. This is valid for all r greater than or equal to s, where obviously s has to be greater than or equal to k, otherwise it will not have meaning. So, if you multiply the whole thing by z power r and then you sum from r is equal to s to infinity, because it is valid for r is equal to greater than or equal to s, you can only start from s and then sum up to infinity. So, we obtain r is equal to s to infinity C naught AR plus C1 AR minus 1, this whole expression, it is multiplied by z power r. Then on the right hand side you have sigma r is equal to s to infinity Fr Zr. Now, take term by term and see how you can rewrite. The first term here will be C naught AR Zr, and you are summing from r is equal to s to infinity. So, you have r is equal to s to infinity C naught AR Zr. What is this? AR Zr is the general term of the generating function A naught, A1, A2, etc. If you call the generating function as AZ, here the first A naught up to A s minus 1, they are missing here. It starts from A s z power s. So, subtracting those from the generating function, C naught is you can take out. So, the rest of it will be sigma r is equal to s to infinity, and that is the generating function where the first s terms starting from A naught to A s minus 1 are missing. So, A z minus A naught minus A1 z minus A2 z squared and so on up to minus A s minus 1 z s minus 1. Similarly, if you look into the second term, this is sigma r is equal to s to infinity C1 AR minus 1 Zr. How can you look into this? R is equal to s to infinity C1 AR minus 1 Zr. The general term in the recurrence in the generating function will be AR minus 1 Zr minus 1. So, take out one z out and C1 also you can take out. So, C1 z if you take out, you get sigma r is equal to s to infinity A r minus 1 z r minus 1. That is the first r minus 1 terms are missing in the generating function. So, that will give rise to A z minus A naught minus A1 z etc. up to A s minus 2 z s minus 2. Similarly, each one of the terms you can substitute, and you can see that sigma r is equal to s to infinity C k A r minus k z r. You take the C k out, you take one z k also out. So, remaining term will be sigma r is equal to s to infinity A r minus k z r minus k, and there is a few terms in the beginning of the generating function are missing. So, it will be A z minus A naught minus A1 z up to minus A s minus k minus 1 z s minus k minus 1. Having written the left hand side like this and then equating summing adding all these things and equating to the right hand side, you get A z will be 1 by C naught plus C1 z plus to C k z k. Right hand side you have the sum from r is equal to s to infinity Fr Zr, but these terms which are there, they have to be, when they are brought into the right hand side, they will become plus. So, you get C naught A naught plus A1 z plus A2 z squared etc. Then C1 z into A naught plus A1 z etc. and so on up to Ck Zk A naught plus A1 z plus A2 z so on. So, you get a very good closed form expression for the generating function, and in general this expression will be such that it will be very easy to find a simple expression for AR. Let us consider a few more examples and solve them by using the method of generating functions. Let us consider the same example which we considered in the last lecture. AR be the number of regions into which the plane is divided when you draw R ovals, each oval cutting every other oval in 2 points. And this is the recurrence relation. We obtained this recurrence relation in the last lecture, and the solution for this is AR is equal to R squared minus R plus 2. This is the answer we got by making use of homogeneous solution and particular solution. Now, let us see whether we can get this by making use of the idea of a generating function. The boundary condition is A1, when you just draw one oval, it divides the plane into 2 regions. So, A1 is equal to 2, A2 is equal to, when you draw 2 ovals, it divides the plane into 4 regions. So, A2 is equal to 4. Now, we can check that A1 is 1 minus 1 plus 2, 2, A2 is 2 squared minus 2 plus 2 is 4, and so on. Now, A0 does not have any meaning, because when you do not have any oval, it does not make any sense, but you choose A0 so that it satisfies this recurrence relation. So, A1 is A0 plus 2 into 1 minus 1. So, A0 is equal to A1, that is equal to 2. A0 does not have meaning, but to satisfy the recurrence relation you can choose it as 2. Now, look at the recurrence relation. Let us find the solution by making use of the generating function concept. AR is equal to A R minus 1 plus 2 into R minus 1. Now, multiply by ZR, then you get AR Z power R equal to AR minus 1 Z power R plus 2 into R minus 1 into ZR. Sum from R is equal to 1 to infinity. So, R is equal to 1 to infinity AR ZR equal to sigma R is equal to 1 to infinity AR minus 1 ZR plus sigma R is equal to 1 to infinity 2 into R minus 1 into ZR. Now, this we have seen is of the form A1Z plus A2Z squared. So, if you represent the generating function for A0 A1 as AZ, this is AZ minus A0, and this again, as in the previous example, the general term has to be AR minus 1 ZR minus 1. So, if you take that Z out, it will be A0 plus A1Z etc., which is AZ. Then this term is, if you take that 2Z squared out, it will be R is equal to 1 to infinity R minus 1 into Z power R minus 2. This is of the form, when R is equal to 1 it is 0, when R is equal to 2, 2 minus 1 Z, 2 minus 2, it will be 1. So, it will be 1 plus 2Z plus 3Z squared plus 4 Z power 5 and so on. So, it will be like that. This expression will be 1 plus 2Z plus 3Z squared plus 4Z cubed plus 5Z power 4 and so on. This you know is 1 by 1 minus Z the whole square. So, making use of that here, you get AZ into 1 minus Z equal to A0 plus 2z squared by 1 minus z the whole square. But we have seen that a naught is just 2 and this is 2z squared by 1 minus z the whole square. So, with this you get the expression for a z like that. A z is 2 by 1 minus z plus 2z squared by 1 minus z the whole cube. This is the generating function for the sequence a naught, a1, a2, a3, etc. Now, the general term is, what is will be the general term zr, that is 2 zr, it should be like that. Here you want to find the term for r, that is 2, you have to find the coefficient of zr minus 2 here, right. You want to find the coefficient of zr minus 2, so that when you multiply by z squared you get zr. But what is 1 by 1 minus z cubed? It is 1 plus 3 z plus 3 into 4 by 2 z squared plus 4 into 5 by 2 z cubed and so on. The general term or the coefficient of z power r minus 2 will be r into r minus 1 into r by 2. So, making use of that here, it will be r minus 2 into r minus 1 into r by 2 zr. The coefficient of z power r here will be this. This 2 and 2 will get cancelled. So, coefficient of z power r, that is ar is given by 2 plus r into r minus 1, which is r squared minus r plus 2. So, the expression for ar is r squared minus r plus 2, which is the same as we got in the last lecture by making use of homogeneous solutions and particular solutions. So, we see how to solve the same problem by means of the generating function method and also by homogeneous solution and particular solution. Let us take one more simple example and solve it in both the ways and see how the answers agree. Consider the Tower of Hanoi problem. What is the Tower of Hanoi problem? You have 3 pegs A, B, C, and in one peg you have discs in the decreasing order. Smaller disc is placed above the bigger disc, and you want to transfer all of them from this peg A to peg B. Intermediately you can use peg C. The transfer should be done in such a way that at no time a smaller disc lies below a bigger disc or a bigger disc lies above a smaller disc. So, if you have A1, that is just one disc, it requires only one transfer. If you have 2 discs like this, say 2 discs like this, first you can put it here, then transfer the second one here, then again transfer this here. So, A2 will be 3. In general, when you have n discs, you transfer n minus 1 of them here, transfer the nth disc here, then transfer again the n minus 1 disc to this place, making use of the remaining peg as the intermediary peg. So, the expression you get is AR is equal to 2AR minus 1 plus 1. This is the reconciliation. And when you have this reconciliation, what is the solution? And you have A1 is equal to 1, A2 is equal to 3. So, what will be the value of A naught? A naught is no disk, so it has to be 0. But let us see, A1 is 1, 2A naught plus 1. So, which gives you A naught is equal to this. This is also meaningful when you do not have any disks, no transfer need to place. Number of steps is 0. So, A naught is 0 in this case. Now, let us see how we make use of the homogeneous solution and the particular solution method to solve this. So, AR minus 2AR minus 1 is equal to 1. So, the characteristic equation is x minus 2 is equal to 0 or x is equal to 2 is a root. So, homogeneous solution is AR is equal to A 2 power R. We have to find the value of A from boundary conditions. Now, what is the particular solution? The right hand side is a constant and 1 is not a root. So, you can take the particular solution in the form P, a constant. So, P minus 2P is equal to 1 or P is equal to minus 1. Okay. So, the total solution AR T, the total solution will be homogeneous solution ARH plus ARP, and that will be A 2 power R minus 1. So, you have the expression for AR as AR is equal to A 2 power R minus 1. You know that A1 is equal to, what is A1? A1 is 1. So, 1 is equal to A 2 power 1 minus 1. So, 1 is equal to 2A minus 1, A is equal to 2A is equal to 2. So, A is equal to 1. Okay. So, the expression for AR is 2 power R minus 1. This is the number of steps required to transfer R discs from peg A to peg B, making use of an intermediary peg C such that at no point of time a bigger disk lies above a smaller disk. The expression is given by AR is equal to 2R minus 1. Let us see how the same problem can be solved by means of generating function method. So, we have to get the answer AR is equal to 2 power R minus 1. So, we start with this recurrence relation. It is valid for R is equal to 1. So, R minus, this is R minus 1. So, multiply by ZR. So, you get AR ZR minus 2 AR minus 1 ZR equal to ZR. Then sum from R is equal to 1 to infinity. So, that will be sigma R is equal to 1 to infinity AR ZR minus sigma R is equal to 1 to infinity 2A R minus 1 ZR is equal to sigma R is equal to 1 to infinity Z power R. So, this you know is AZ minus A naught, and this is 2Z AZ, 2 you take out and then AZ DZ equal to, this is Z by 1 minus Z, because Z you can take out, then it will be a sum 1 plus Z squared, which is 1 minus Z. Now, this becomes A naught is 0. So, this becomes A Z into 1 minus 2 Z equal to Z by 1 minus Z, or A Z is equal to Z by 1 minus Z into 1 minus 2 Z. So, resolving into partial fractions, let Z by 1 minus 2 Z into 1 minus Z be equal to sum A by 1 minus 2 Z plus d by 1 minus z. So, in this case z is equal to a into 1 minus z plus b into 1 minus 2z. Equating the constant terms, a plus b is equal to 0. Equating the coefficient of z, you have minus a minus 2b equal to 1, or a plus 2b equal to minus 1, a plus b is equal to 0, subtract, you get b is equal to minus 1. And because a plus b is equal to 0, a is equal to minus b are 1, a is 1 and b is 0. So, you get a r, a is the generating function as 1 by 1 minus 2z minus 1 by 1 minus z. Now, for the solution you have to find the general term. One by 1 minus 2z will be 1 plus 2z plus 2z the whole squared plus 2z the whole cubed and so on. So, general term is 2 power r z power r. 1 by 1 minus z is 1 plus z squared and so on. So, the general term is z power r. So, if you take the coefficient of z power r in A z, the first term will contribute to 2 power r. So, A r, that is the coefficient of z power r, that the first term will contribute to 2 power r, and you have a minus here, minus in this place. So, minus the coefficient of z power r in the second term, that is 1. So, the expression you get is A r is equal to 2 r minus 1, which is the same as we obtained in the earlier case. So, the same problem we have solved by making use of homogeneous and particular solutions. Then also we get the same answer by the method of generating function also we get the same answer, but the generating function method is much more elegant than the earlier one. Sometimes we get generating equations of this form. A r is equal to 3 a r minus 1 plus 2 b r minus 1, b r is equal to a r minus 1 plus b r minus 1. Here there are two variables, you have to solve for both a r and b r. Here the method of generating function comes in handy, we can solve in a very elegant manner making use of generating functions. The boundary conditions are given like this, a naught is equal to 1 and b naught is equal to 0. The boundary conditions are given like this. Now, we again use the same method, multiply by zr. So, ar zr is equal to 3 ar minus 1 zr minus 1 plus 2 br minus zr, this is zr, br minus 1 zr, and summing from r is equal to 1 to infinity, this is ar zr is equal to sigma r is equal to 1 to infinity 3 ar minus 1 zr plus sigma r is equal to 1 to infinity 2 br minus 1 zr. Now, similarly, you will also get sigma r is equal to 1 to infinity br zr equal to sigma r is equal to 1 to infinity ar minus 1 zr plus sigma r is equal to 1 to infinity br minus 1 zr. Rewriting this, if az is the generating function for a naught, a1, etc., and Bz is the generating function for B0, B1, etc. Then these two equations become Az minus A0 equal to 3 times Z, take out that Z, then you get 3Z Az plus 2Z Bz. And the second equation, this equation, it becomes Bz minus B0 equal to Az Zaz plus Z Bz. A0 is 1 and B0 is 0 by the initial condition. So, you have Az minus 1 is equal to 3Z Az plus 2Z Bz, and Bz is equal to Zaz plus Z Bz. Writing it as simultaneous equations, you get Az into 1 minus 3Z minus 2Z Bz equal to 1. The first equation becomes like this. Second equation becomes Zaz minus Zaz minus Bz into 1 minus Z equal to 0, or Zaz equal to 1 minus Z Bz, or Bz is equal to Z by 1 minus Z Az. Make use of this in the first equation. So, you get Az into 1 minus 3Z minus 2Z. Instead of Bz, again you can write this, it will be Z by 1 minus Z Az equal to 1, or you get Az into 1 minus 3Z into 1 minus Z minus 2Z squared Az by 1 minus Z equal to 1, or Az into 1 minus 3Z minus Z plus Z 3Z squared minus 2Z squared equal to 1 minus Z, or Az is equal to 1 minus Z by 1 minus 4Z plus Z squared, and Bz is Z by 1 minus Z Az, that is Z by 1 minus Z into 1 minus Z by 1 minus 4Z plus Z squared. This will get cancelled, and so you get this equal to Z by 1 minus 4Z plus Z squared. So, the expression for Az is this and B is Az is this. The expression for Bz is this. Having obtained this, can you get the value of AR and BR? Now, this is a quadratic expression. You have to resolve into partial fractions to get the roots. So, 1 minus 4Z plus Z squared, what are the roots? The roots are given by 4 plus or minus square root of 4 squared minus 4 by 2, that is 2 plus or minus square root of 12, 12 by 2, which is 2 plus or minus root 3. So, having obtained like this, First let us solve for A. Az equal to 1 minus z by 1 minus 4z plus z squared. This you can write as A by 1 minus 2 plus root 3 z, resolving into partial fractions you can write like this, plus b into 1 minus 2 minus root 3 z. Now you have to find the value of a and b. How do you find that? 1 minus z equal to a into 1 minus 2 minus root 3 into z plus b into 1 minus 2 plus root 3 into z. So, equating the constants, a plus b is equal to 1. This is equating the constants. Then equating the coefficient of z, you have minus 1 equal to a into minus 1 into 2 minus root 3, that is minus a into this, again minus b into 2 plus root 3. This is equal to, so 1 equal to, if you remove the minus sign, it will be a into 2 minus root 3 minus plus b into 2 plus root 3. Now making use of this, a is 1 minus b, so 1 is equal to, a is 1 minus b into 2 minus root 3 plus b into 2 plus root 3. Let us simplify and see what we get. Get 1 is equal to 2 minus root 3 minus b into 2 minus root 3 plus b into 2 plus root 3. If you take the b here, b into 2 minus root 3 minus 2 minus root 3 equal to 2 minus root 3 minus 1, that will be b into, this will get cancelled, minus 2 root 3 equal to 2 minus so b will be root 3 minus 1 by 2 root 3, multiplying by root 3 you get 3 minus root 3 by 6. The value of b you get as 3 minus root 3 by 6. The value of a is 1 minus b, that is given by 1 minus 3 minus root 3 by 6 is given by 6 minus 3 plus root 3 by 6 is 3 plus root 3 by 6. So, the expression becomes the value of Az is given by 3 plus root 3 by 6 by 1 minus 2 plus root 3 into z plus b by etc. b is 3 minus root 3 by 6 by 1 minus root, there is one minus sign missing. See, this is okay, correct, this is correct. So, this will be 1 minus 2 minus root 3 z. So, the general term will be and coefficient of z power r will be 3 plus root 3 by 6 and 2 plus root 3 to the power of r plus 3 minus root 3 by 6 and 2 minus root 3 power r. This will be the coefficient of z r. So, this is the expression for AR. AR is given by this. Let us check for the value of r is equal to 0. The boundary condition is A naught is 1. See whether it works out. Put r is equal to 0. This is 1, this is 1. So, you get A0 equal to 3 plus root 3 by 6 plus 3 minus root 3 by 6 equal to 6 by 6 equal to 1. A naught is 1. That is what we have taken as the boundary condition. It verifies here. So, similarly, you can also find the expression for Bz. Now, Bz is given by z by 1 plus 1 minus 4z plus z square. And so, making use of partial fractions, this can be written as a by 1 minus 2 plus root 3z plus b into 1 minus 2 minus root 3 into z. You can write this way. So, that means z is equal to a into 1 minus 2 minus root 3 into z plus b into 1 minus 2 plus root 3 into z. Equating the constants, a plus b equal to 0, this is constants, and considering the coefficient of z, minus a into 2 minus root 3 minus b into 2 plus root 3 equal to 1. So, from the first one a is equal to minus b, make use of that here. A is minus b, so minus a will be b. So, b into 2 minus root 3 minus b into 2 plus root 3 is equal to 1, or b into 2 minus root 3 minus 2 minus root 3 equal to 1, minus 2 root 3 b equal to 1, or b is equal to 1 by 2 root 3 with a minus sign, and a is minus b, that is 1 by 2 root 3. So, this you can write as multiply by root 3 and write it as root 3 into 6, multiplying the numerator and the denominator by root 3, you get this. Similarly, this is minus root 3 by 6 and this is root 3 by 6. So, with this result, Bz is taken to be, we have seen that Bz is a by 1 minus root 3z. So, here a is root 3 by 6. So, root 3 by 6 by 1 minus 2 plus root 3 z minus, again same thing, root 3 by 6 by 1 minus 2 minus root 3. This is the generating function for Br. Bz is the generating for the sequence B0, B1, B2 and so on. The general term here will be root 3 by 6 and 2 plus root 3 power r, z power r, and the general term here will be again root 3 by 6 and it is 2 minus root 3 power r, z power r. So, the coefficient of z power r is the value for AR. So, AR is given by root 3 by 6 into 2 plus root 3 power r minus root 3 by 6, 2 minus root 3 to the power of r. I am sorry, this is BR, expression for BR. So, BR is this. Let us take the value for B0 when r is equal to 0. B0 is, this is just 1, this is just 1. So, you get root 3 by 6 minus root 3 by 6, which is equal to 0, which verifies with the initial condition that B0 is 0. So, the expression for BR is this: AR equal to 3 plus root 3 by 6, 2 plus root 3 to the power of R plus 3 minus root 3 by 6 into 2 minus 3 power R, and BR is given by this expression. So, the method of generating functions comes very handy in solving such simultaneous equations in recurrence relations. In general, these recurrence relations are very useful in analyzing the complexity of an algorithm. Most algorithms, if you have a size of n, it will be divided into 2 problems of size n by 2. You solve the problems of size n by 2 and then do some other operation to merge it. For example, take merge sort, you divide into 2 halves, then sort each one of the half, then merge it and so on. So, in such cases, if the complexity is given by Tn, when the size is n, the time of solving the problem, time complexity of solving the problem is Tn, say, then it is divided into 2 sub problems of size n by 2. Apart from that, there will be some more operations to get the whole solution. So, that is given by 2 times T n by 2 plus something. That could be order n or order n squared and so on. Suppose this is of order n, the other operation involving finding the solution for the whole problem given the solution of 2 sub problems, if it is of order n, then by usual method you will find that the solution to this will give you that Tn is of order n log n, Tn. That is, there will be some constants, and those constants we need not very much worry about. In the big O notations, constants are not really considered. So, if you have a recurrence relation of this form, order n, this is say some k times n, where k is a constant and n, then the solution for such a recurrence relation will give you that Tn is of order n log n. Such things are very useful in analyzing the complexity of an algorithm. So, recurrence relations play a very important role in many of fields in computer science, especially in analysis of algorithms, and we have seen how recurrence relations can be solved by 2 methods. One is by the method of homogeneous solution and particular solution and adding them up, and another is by means of the generating function approach. So, next we shall consider some other topics like algebras and so on in the coming few lectures.